What is up, Adwaiters? Welcome back to the channel. I'm your host Jatin Kumar Malik, and we are back at it again today at Advent of Code 2024. And yesterday we tackled this really interesting problem known as keypad conundrum, where we solved a series of robots that were giving instruction to each other in a sequential manner. And we learned how the sample space can sometimes become too large for you to just brute force it, and how finding a small sub problem is the key in questions like this, where it is a dynamic programming question. And I hope you were able to get some really good takeaways from that. And if you are just joining us, make sure to check out all the action from day 1 to day 21 here in this playlist, which is linked above, or it's linked below in the description. And based on what device you are watching this video on, you may or may not be able to observe that I am presenting to you this video from a 22-sided polygon camera frame, which is also known as an icosahedron. And yeah, that's a mouthful. And it is almost close to being a full circle. And we have been talking about this and debating about when the camera frame will have enough sides that it almost looks like a circle. But yeah, with that, let's dive into today's problem. So today it's day 22, and our problem is called money market. Let's read it. So as you are all teleported deep into the jungle, a monkey, which is a reference to 2022 day 11, steals the historian's device, and you will need to get it back while the historians are looking for the chief. And here, I think from day 1, we have been looking for the chief historian, which has gone missing, and we really need him to save the Christmas. So let's read further. The monkey that stole the device seems willing to trade it, but only in exchange for an absurd amount of bananas, of course. Your only option is to buy bananas on the money exchange market. So we have something known as money exchange market, from where we can buy bananas. And we have to give this bananas to a monkey. This may or may not be relevant for the question, but I just like writing things down sometimes. So you aren't sure how the money exchange market works, but one of the historians senses troubles and comes over to help. Apparently, they have been studying these monkeys for a while and have deciphered their secrets. Today, the market is full of monkeys buying good hiding spots. So now it seems like if we keep expanding our association graph here, that monkeys are very interesting in buying good hiding spots. Okay, so we will call this GHS in short. And fortunately, because of the time you recently spent in this jungle, 2022, you know lots of good hiding spots you can sell. If you sell enough hiding spots, you should be able to get enough bananas to buy the device back. Okay, so it seems like I have to sell some good hiding spots to these monkeys. On the market, the buyer seems to use random prices. So here, like we have a bunch of buyers, and they are using some kind of a random price. But their prices are actually only pseudo-random. Interesting. So pseudo-random is a technique where there is a function that is generating random words, which it may seem like random, but it is not actually completely random. So it's like as the Wikipedia mentions here, it's the deterministic random bit generator. So it's basically an algorithm whose properties approximate the properties of sequence of random number, but it's actually not random. And you can write a lot of pseudo-random functions here, like where there can be an example to an untrained eye who doesn't know even, let's say, a Fibonacci sequence or a prime number generator. It may seem very random to them, but only if you know the order that like how it is being generated, it's very easy to predict what number is next. And if you know the secret of how they pick their prices, you can wait for the perfect time to sell. Makes sense. We would like to sell on like very high prices so that we can get bananas, so that we can get back the device that is stolen by monkeys. And the part about the secrets is literal. The historians explains each buyer produces a pseudo-random sequence of secret numbers where each secret is derived from the previous. Okay, so it seems like we have a buyer and they are producing a sequence of, so like a list of secret numbers where each secret is derived from the previous. And it's funny, I gave an example of Fibonacci because Fibonacci sequence is almost always like that, where it depends on the previous number. But let's read further. In particular, each buyer's secret number evolves into the next secret number in the sequence via following process. So we are given a process. I'll just make some space here so that we can write it. So it says that you need to calculate the result of multiplying the secret number by 64. So let's assume that you are given a secret number. Let's call it Sn. So I think we are given the process here. So in first step, you multiply the secret number by 64. So let's say Sn multiply by 64. And then mix this result into the secret number. And then we are doing some process of mixing this back into secret number. Okay. And finally, prune the secret number. And finally, I don't know what these things means, but I'm going to write that. We want to prune the secret number. And in the second step, it is saying that calculate the result of dividing the secret number by 32. So we are going to divide the secret number by 32. Round the result down to the nearest integer. So since I'm using Python, I can just do this double divide and it will round it up automatically. And then mix this result into a secret number. And then it is again saying that we have to mix this result into a secret number. And finally, prune the secret number. So we are doing the same thing again, where we are again doing a prune process to a secret number. Okay. And then there is the third step, which says that calculate the result of multiplying the secret number by 2048. So we are again doing, so it's basically like your algorithm that is given to us. So 2048. And then mix this result into secret number and finally prune the secret number. So it's following the exact same process where we mix this with secret number and then we do some kind of a prune process on secret number. So, okay, so it seems like a 3-step process. And interestingly, these pseudo-random numbers are often used in cryptography and also like to encrypt and decrypt things, because usually it uses a seed value or a key in a way that can allow you to decipher the process exactly how we are doing here. So here, instead of knowing the key, we know the algos, and I'm hoping we would know some kind of an initial key also. So reading further, each step of the above process involves mixing and pruning. And now they tell us what that is all about. So let's write it down below. So I'll make some space. And first, let's talk about mixing. So what does mixing means? So to mix a value into the secret numbers, calculate the bitwise XOR. So bitwise XOR. So in, I think, few episodes back, I explained what do we mean by XOR. And I even have a short video to quickly explain that, but in like very TLDR way. So XOR is exclusive OR. Like whenever we have 2 bits given, we do an exclusive OR that it should be not the same. Exactly, it always give a true value where neither input or nor output is same. And I think I will put like a truth table here so that it's easy for you to understand. But let's read further. And yeah, XOR is denoted in programming. XOR is denoted by this tilde sign. So if you open your Python terminal, you can directly just type 2 numbers and you can do a XOR. And even if you type decimal numbers, it first converts it into a binary and then do a XOR operation. And this is also often used in our cryptography operations and encryption operations. So it says that calculate the bitwise XOR of the given value and the secret number. So we have something known as GV, which is the given value. And we have to do a bitwise XOR with our SN, which is the secret number. And then the secret number becomes the result of that operation. I see. If the secret number is 42 and you were to mix 15 into the secret number would become 37. And it's exactly doing a XOR operation, I guess. So if we were to open a terminal and do 42 XOR 15, it should give us 37. And I'll put like a screenshot of my terminal here. And similarly, we have another process. So this was mix, and the other process is called to prune. And whenever you prune a number, so here we were giving like you are mixing this into this. So I think this becomes our GV and this is the SN. And then we are just pruning the secret number. So to prune the secret number, calculate the value of secret number modulo 16,777,216, which is 16,777,216. And I also, in the last video, like couple of videos back, I explained what modulo mean. So modulo is often denoted by the percentage sign. And what happens is if you do x modulo y, it gives you the output of remainder of that equation. So if you were to divide x by y, whatever would be the remainder. For example, if you do 5 modulo 2, the answer would be 1, because when you divide this, it's 2 into 2, 4, and your remainder is 1. And similarly, if you do 2 mod 2, the answer would be 0, because it is perfectly divisible. So in this case, it says that you take the secret number and you mod it with 16,777,216. And then the secret number becomes the result of that operation. So you basically assign it back to the secret number. That makes sense. And if the secret number is, I think they're given an example where we are given a value of 100 million. So if you were to prune the secret number, then it would become this number right here, 1611392, which is basically the remainder of the equation using the modulus. So reading on, after this process completes, the buyer is left with the next secret number in the sequence, and the buyer can repeat this process as many times as necessary to produce more secret numbers. So if a buyer has a secret number of 123, their next 10 secret numbers would be this. And I think we should definitely do a dry run here to make sure that we understand the problem really well. And it is always very, very good to first take the test case and try to write it down with a pen and paper and try to see if you understand the logic behind it. Writing code is usually the easy part. So what we are done is we are here given a secret number that is equal to 123. And let's see what we have to do here. So first, let's do it in multi-stage operation. So in the first step that we wrote here, I will just read it from the right side. We will multiply the secret number by 64. So if I do that, 64 multiplied by 123, we get 7872. So we get, so we do 123 multiplied by 64, we get 7872. And then we have to mix this result into the secret number. So this was our secret number and this is our result. So we have to now do 123 mix 7872, where our mix means nothing but a bitwise XOR. So I'll just open our terminal quickly and do that. So 123 XOR 7872. This gives us a value of, so this is the, this is the XOR, and this gives us a value of 7867. So we get 7867. And I think it mentioned here, then this finally, and then finally prune the secret number. And I think this becomes the secret number, right? So if the secret number is 42 and you were to mix 15 into the secret number would have become this. So this is our new value of secret number. And then in the next step, when you do a prune on it, in the prune, remember, we had to do the modulo by this value right here. So since this number is smaller than 7867, I think our answer 7867 mod this number would still remain same, because there is no quotient when you divide 7867 by this number right here, 16777,216. So our answer is 7867 on the first part. And then this becomes the secret number. So now my secret number is pointing to this. So in the second phase of operation, it's like a pipeline. It reminds me of an ETL pipeline where you're doing extract, transform, load. It's a very popular pattern in databases. But it says that calculate the result of dividing the secret number by 32 and round it to nearest integer. Now we have to do 7867 divided by 32. So this gives us an answer of 245. And then mix this result into the secret number. So our secret number was this, our result was this. So now I will do 7867 and mixing is XOR 245. And this should give me an answer of 7867 67 XOR 245. I get an answer of 7758. So we get an answer 7758. And then this becomes our new secret number. And then we have to prune this result. So when you prune this, you do a mod by this. Remember, if you're modding anything by a larger value, this will still be same. So once we do the prune, this still remains 7758. Let's make some more space for the third phase. And now this is our secret number. And in the final third phase, we have to calculate the result of multiplying the secret number by 2048. So let's do that. 7758 multiply by 2048. This gives us a value of, so I'll write it here, 1588384. So 7758 multiplied by 2048 gives us a value of 1588384. 1588384. That's a big number. And after you do that here, then mix this result into the secret number. So now this is our result. This was our secret number. So in the next pass, I will go 7758 XOR 1588384, and we get a value of 1588790. So 1588790. And in the next step, we have to prune this. So this becomes our new secret number. And when we prune this, we do a mod with this 167777216, which is still larger than this number, I guess. But I'll still do it. 1588790 mod this. And yeah, it has larger value. So after also pruning, we get back the same result. And if you see here, the next secret number is exactly this value, 1588790, which is what we got here. So it seems like we understand the question well. And this is the most critical step of solving this question. And if you don't get it, I would recommend you to go back and watch this again and pause the video and then try to do it yourself with your hand. And this will help you build a solid understanding. And here, if you see, like now I have everything I need to do to find the next sequence number. So it seems like we are doing this again and again to find these 10 secret numbers. So if we were to now start the whole process, this 3-step process again, we will probably get this next number, which is 16495,136, and so on. So let's read forward. What do we have to do? So we have to keep doing this like for the nth time. But anyways, each buyer uses their own secret number when choosing their price. So it's important to be able to predict the sequence of secret numbers for each buyer. So each buyer basically has their initial secret number, like similar to how we were given this 123. And then it is important to be able to predict the sequence of secret numbers for each buyer, which we can now do. Fortunately, the historian's research has uncovered the initial secret number of each buyer. So this is basically like the value at T0. And they are given an example where if there were 4 buyers, we are given 1, 10, 100, and 20, 24. So like we are given 1, 10, 100, and 2024. And this is buyer 1, buyer 2, buyer 3, and buyer 4. And this list describes the initial secret number of 4 different secret hiding spot buyers on the Monkey exchange market. Was it Monkey or it's Money? I think we probably read it wrong. It's Monkey exchange market, but MEM for short. It doesn't really matter. It's just the syntax around the problem. The core of the problem is something very different, but yeah. And if you can simulate the secret number from each buyer, you will be able to predict all of their future prices. Sure. In a single day, buyers each have time to generate 2000 new secret numbers. In this example, for each buyer, their initial secret number, which is given here, 1, 10, 100, and 20, 24, and the 2000th new secret number they would generate are. And then what we are given is, basically we did this for 2000 times, this whole process of the 3-stage process of getting the next secret number, and their 2000 secret number was given here. So this was 8685429. Similarly, this was 4700978. And this was 15273692 and 8667524. I hope I'm not making a mistake. And then it says that adding up the 2000 secret number for each buyer produces. So what we did is we calculated this and then we are doing a sum of this. And this produces a value of 37327623. And that's our answer for this puzzle. So for each buyer, we have to simulate looking at the puzzle input where we are given these values, which is the initial seed value. Simulate the creation of 2000 new secret numbers. And what is the sum of 2000 secret numbers generated by each buyer? And if I look at my puzzle input, we are given like a huge number of buyers where we have to run this process and do this. And that's our question. So I think now is a good time for you to pause and think before we move over to the hints that how will you approach this problem and how will you approach the logic of solving this problem. And once we are back, we will discuss some of the hints and how I'm thinking of writing some code for this. I'll see you in a bit. Okay, so are you ready to tackle this monkey business? Well, here are a couple of nudges in the right direction and no spoilers, I promise. So let me make some space. And in this question, if you again read, I think that has been the theme, and I have been saying this every time we discuss hints, that there is a lot of misdirection and complexity around monkey exchange market and like your bananas and things that have been lost. But that is all part of a narrative in the story. As a part of a good software engineer, your job is to identify the hidden logic deep beneath the problem so that you can write down code and solve that. And in this case also, I think one of the first things that you have to do is you have to focus properly on doing this 3-stage process that we wrote above here. This 1, 2, 3, I think I explained it here very well, and which involves this mixing and pruning. And I think this is the core of the problem. You need to have a function that can take a number and it can do this 3-stage process and then produce the next number. And in this one, you have to, if you notice, we are doing multiply, XOR, and modulo 3 times in different stages where like this changes, and this changes. So that helps you think and follow this popular technique called try, do not repeat yourself, where you can just write one function and then all you need to do is call it in a sequence 3 times with different operators, different operands here. And once you do that, you have to think about how you're going to store and update secret number after each iteration. And in this question, I think it's always good to see what you need. So we don't really need to store the intermediate secret number. It seems like we directly have to store the 2000 secret number. So probably your space complexity would be O1 into n, which is the number of buyers, which would be O of n. Like you just need to have one variable for each buyer and you just need to update them in a row. And to do this, one of the simple things that comes into my mind is just maintaining a list. You can also maintain a dictionary, but using a list, you can be very clever and based on how you are reading your input, you can just assign the same index of the initial seed number into your list, and then you iterate through your list, do a 3-step process 2000 times, and like you will have your answer. And I think, this is pretty much it. And I would highly recommend you to pause the video here, grab your favorite beverage or maybe some actual bananas for inspiration and try to implement the simulation. And it should be pretty simple. Once you have nailed down writing this function, I think doing a loop over a list of size 2000, or not 2000, a list of size n 2000 times should be fairly quick for your computer to do. And with that, I'm also going to go ahead and write some code, and I will see you in a bit. And hey, welcome back. And as you can see, we have received our first gold star for the part 1. And I hope you were also able to solve your answer through some of this language madness that was there. And I followed exactly what we discussed here in the hints. And essentially, I created a function, as I mentioned here, that takes a secret number as an input and does all these three operations and returns the next secret number in the sequence by performing this multiply, mix, and prune, which is multiply, XOR, and modulo step. And then I did this for the whole list of our the buyers that were given, that I was maintaining it in a one-dimensional array or a list. And then for each initial secret number from the input, we ran the loop of this function in a loop 2000 times, and I kept track of this final secret number generated after each function was executed, and then we kept updating that. And after 2000 iteration, because we had to get the 2000th result, I just summed up my whole array and got the answer. And I think I have a fairly new machine, but it still took me less than 1 second to find that. It may vary for you based on what language you are choosing, but it should still be fairly quick. So one thing that was very interesting and I had to double check was this value. I actually missed 1.7 while I was inputting in my code, and I spent some time debugging that test case because the flow of the program was absolutely correct. And then I had to go back, read my question once again, and I found that, oh, I missed 1.7. But after that, I think it was a fairly smooth sailing. And with that, I think we can move over to part 2. But before that, hey, if you're finding these walkthroughs helpful and are enjoying our coding adventure together, smash the subscribe button below and join this awesome community. And it's absolutely free. I have zero snake oil courses. I have absolutely nothing to sell it to you. And if you subscribe, you will basically get notified for every video that I make. And I have a few videos in pipeline where I want to share some deep insights from my 15-year-old long career. So it should probably be helpful and you might get to learn a thing or two. But yeah, with that, let's go back to the part 2. So looking at part 2, reading it. Of course, the secret numbers aren't the prizes each buyer is offering. Remember, we had to sell them so that we can get some bananas and we can give it to the monkey so that we can get our historian device back. Well, that would be ridiculous. Instead, the prizes the buyer offers are just the one digit of each of their secret numbers. So if the buyer starts with the secret number 123, the buyer first 10 prizes would be these. And how are we calculating these? Oh, okay. I remember calculating this value, right? So if we were given the initial secret number as 123, we had this sequence that we calculated above in the part 1. I just copied it from there. And it seems like the prize would be the last number, the last digit of your secret number. So in this case, we are given prizes where it is 30654464424. And I'm just taking it from here, these numbers that are given to us, the last one. And so it says that it's calculating like that. And this price, so this is the price, the last digit, is the number of bananas that buyer is offering in exchange for your information about a new hiding spot. However, you still don't speak monkey. And I think this is again a reference back to 2022. So you cannot negotiate with the buyer directly. So this is the price of the buyer that they are offering in exchange for your information. And we don't speak monkey, but historian speaks a little, but not enough to negotiate. Instead, he can ask another monkey to negotiate on your behalf. Unfortunately, the monkey only knows how to decide when to sell by looking at the changes in the price. Specifically, the monkey will only look for a specific sequence of 4 consecutive changes in the price and then immediately sell when it sees that sequence. So very interesting. So to negotiate, we can get one monkey, but it seems like monkey has a memory of seeing only 4 consecutive prices, is it? Changes in prices. So it can only look at this, which is the delta of changes in prices. And let's see how that is being calculated. And then immediately sell when it sees the sequence. Okay. So if a buyer starts with the secret number of 123, the buyer first 10 secret numbers, prices, and the associated changes would be 3065. That is there. Oh, and in the bracket, then it is writing the difference. So if I use some other color, we can see that our differences are here. So this is the delta. It's like a cumulative delta from the previous instruction. like whenever we are calculating it. So 0, 2, -2, 0, -2, and they have not given it, but since we wrote this, it can write it like +2. And this was first 10, but this I think is the 11th value. Fair enough. So we are given these, this is like the delta from the previous price. So delta from n-1 in simple terms. So note that the first price has no associate change because there was no previous price to compare with. So 123, if we are starting with it, there is nothing. So we will not take it. In this short example, within just the first few prices, the highest price would be 6. We can see that the highest price is given here, which is 6. But the monkey will not be, so it would be nice to give the monkey instructions that would make it sell at that time. But the problem is that the first 6 occurs only after 2 changes. So there is no way to instruct the monkey to sell then. Oh, so we cannot sell this because there are only 2 instructions that has happened. But the problem is, if you look here, the monkey needs 4 instructions. So they basically need like A, B, C, D. And when they see all 4 instructions together in a sequence, it will sell on the 4th instruction. So, but then the second 6 occurs after the changes -1, -1, 0, 2. So if you look here, here is the second 6, which I think is the highest price. Yes, it is the highest one. So we are optimizing because we want to have, we want to maximize for the price that we can sell our information at. And this 6 comes after this sequence of 4 values, which is -1, -1, 0, 2. And so if you give monkey that sequence of changes, so if I were to give this to here, to this monkey, it would wait until the first time it sees that sequence and then immediately sell your hiding spot information at the current price, winning you the 6 bananas. So I was correct. As soon as it sees this pattern, this sequence, this reminds me of that onsen problem where we were doing the towel patterns, but this is something interesting. So as soon as it sees this sequence, as soon as it sees the last 2, which is pointing to the 6, like 4 + 2, it will immediately sell your hiding spot information, winning you 6 bananas. Okay, so each buyer only wants to buy one hiding spot. So this was our one buyer. So each buyer only wants to buy one hiding spot. And after the hiding spot is sold, the monkey will move on to the next buyer. If the monkey never hears the sequence of price changes from a buyer, the monkey will never sell and will just instead move on to the next buyer. So here this was assuming buyer 1. We have a list of buyers in our input up to buyer n. And it seems like we can only give one sequence to the monkey because we cannot change the sequence for the buyer, because it says that the if monkey never hears the sequence of price changes, the monkey will never sell. So it will, this is like a hard-coded sequence. I'm using programmatic terms, but that does make sense. But let's read forward. Worse, you can only give monkey a single sequence of 4 price changes to look for. You cannot change between the buyers. So yeah, of course, this is hard-coded. So once you give the sequence, this will apply to every buyer there is till b into n. And if it doesn't find the sequence, it will just skip it. But what is our sample space? Let's see. You are going to need as many bananas as possible. Yeah, so our goal is to maximize bananas. We have a simple goal. And so you will need to determine that which sequence of 4 price change will cause the monkey to get you the most bananas overall across all the buyers. And each buyer is going to generate 2000 secret numbers after their initial secret number. So for each buyer, you will have 2000 price changes in which your sequence can occur. So interesting. So here, if you see, we were doing just 10. In our question, it is saying that for each buyer, you will generate 2000 sequences, which means that you will have 2000 price changes that we wrote here with the blue color, this one. So you have 2000 price changes. And what you have to do is that you have to find the one common sequence, the golden sequence that your monkey will look for. So A, B, C, D. And that should apply for all the buyers. That will help us to maximize our number of bananas. This is a really interesting problem. And we are given an example where it says that suppose the initial secret number of each buyer is 1, 2, 3, and 2024. There are many sequences of 4 price changes that you could tell the monkey. But for these 4 buyers, the sequence that will get you the most bananas is -2, 1, -1, and 3. And using that sequence, the monkey will make the following sales. And the most interesting part is that since we have to maximize for bananas, I think we have to ensure that whatever sequence we find, it gives us the maximum number of results across all the buyers. And in this example, we can see that it gives us a sample sequence of -2, 1, -1, 3. And it says that for the buyer with the initial secret number of 1, the changes will occur when the price is 7. And for the second one, it will occur when the price is 7. And for the third one, it will not occur within the first 2000 changes. We will just ignore that. And for the buyer starting with 2024, this changes first occur when the price is 9, which means that the maximum money that we can make from the best sequence across these 4 buyers is 7 plus 7 plus 9, which is 23 bananas. Fascinating. So there are cases where you will probably not find anything from a few ones, but still get the best possible number. So now our answer here is to find the best sequence of this 4 continuous price changes that we can give to our monkey across all B1 to Bn buyers for up to 2000 sequence numbers or prices that are there to find that. And yeah, by sequence to tell monkey, looking for the same sequence of changes, what you can get, what is the most number of bananas you can buy. Very fascinating. So although it hasn't changed, the puzzle input is still the same, of course. Nice. So I think very, very interesting problem. This is very impressive and it builds very nicely on top of our part 1. But yeah, with this, I think I will suggest you to pause here and think, grab a paper, a pen, write it down and think about how you will modify your part 1 to solve for this one and what overall approach you would follow. And in the last 21 days, we have had some questions that were like this, but this is still a very unique question. But there are some of the approach that I discussed that we can reuse here. And once you're back, I will share some of the hints in how I am planning to approach this problem and how you can do that and write some really good code for this. And I'll see you in a bit. And yeah, if you're looking for some hints, let's talk about what I am thinking here. So I'll walk you through my mental model. I think one of the most interesting things is that we need to find a way to generate not just the secret numbers that we were doing in part 1, but we also need to generate the sequence of prices. And as we are generating the sequence of prices, we also need like another, I'm just doing a list, but it doesn't have to be. You need like a delta of price, which is the price change between the n, in minus 1. And we need to do this up to 2000 times for each buyer, which is a lot of sample space, but it is still not unmanageable type of data. But I think the second most important point is that you need to think of how you can systematically, and this is the part where I think the complexity just explodes. How can you systematically try sequences? And your sequence is basically like a window here, which is 4 changes long. And you need to do this across 2000 buyers for their, no, not 2000 buyers, sorry. You need to do this across n buyers. And in my puzzle input, I took a peek to see, we have around 2500 buyers, just to see an idea of the scale we are dealing with. So for 2500 buyers, for each we have 2000 price changes, and we have like a window of 4, which gives us, like if we were to think about this, which gives us 1996 sequences per buyer to check, because we will ignore the first four, because it will only start from the fourth one and then we will go on till that. Or in a way, you can say we will skip the last four numbers because they will not have the four, this based on how you put this and how you think about this. And then you need to check this possibly for 2500, for 2000, for these numbers of combinations. It is a fairly large number, but I think we should be able to brute force it, but it will still take a lot of time. But let's first lay out all the things we know. And I think the hint 3 is that for, if I read the question, for each potential sequence of 4 changes, we will need to simulate the negotiation, the monkey behavior for every buyer and calculate the total bananas earned. And I think that's what makes it much more complex, because you have 1996 sequence per buyer, and where there might be some common ones and there will be some uncommon ones. But whenever you pick one sequence, you have to run it through all 2500 buyers for their all 2000 sequences, which makes it incredibly hard. So you have to basically check for around 2000 sequence for 2000 changes for 2500 buyers. And you have to do it multiple times at a window of 4 characters at one time. And I think this is the interesting part, because I think one thing I was able to quickly see is that when we talk about the price change, since the price is always the last digit of your sequence number, which is your, in a way, sequence number mod 10, because anytime when you divide a number by 10, the remainder is like the last digit, your price change will always be between -9 to 9, somewhere in between that, where you have to calculate that. And I was thinking that for each of the sequence, when we iterate through the buyer's price change, like how we can do this. And one initial way is to just brute force it, which I'm going to definitely try to do. But this also made me think about what else can we think. And based on the last few days, I think we have discussed some approach. So I think one approach that came to initially my mind was divide and conquer. And this should definitely be possible, that I can basically generate multiple threads, like we can use some kind of a multi-threading, and we can generate multiple threads and we can just try out each combination individually. But this is just like a bit optimized version of brute force, because again, we are not doing anything special. The second thing that I was thinking about was like, can we do some kind of heuristics here? And heuristics in a way is that since we have to maximize our profit, the prices, can we try to find out, like maybe maintain the prices for each buyer in like a descending order, where when we are trying our 4-digit combination, we do like a bit of a greedy approach, where we find the maximum highest price for buyer 1 and take the value, the position, like let's say if it is I position, so my I position, I -1, I -2, and I -3, take that sequence and then run through all of that. But then I quickly thought like this will again, in worst case scenario, end up taking exactly same time as brute force, because it is not guaranteed that if you're picking a best value for one buyer, that sequence would mean anything for the rest of your n-1 buyers. And then it struck me, I think, as I was looking into it, I think there is a very interesting concept called MapReduce, or in a simple words, layman terms, we can call it like pre-computation. And I started looking at the data that we need, and I think this is still a theory. I will probably test it after I discuss this with you, and then we'll come back to say in the retro if it worked or not. But looking at the example that was given to us, we can see that there are a bunch of sequences that will be common for most of the buyers. That will give us the answer, which means that even if we have X buyers and they have Y prices across them, the number of total sequences will still be less than X into Y. It's not, because not all buyers have unique sequences. There are some sequences that are common. So what I thought is that what happens if I maintain a map or dictionary, if you're using Python, dictionary of all sequences. So a master dictionary. So not just for one buyer, but for everyone, where my key comma value, and here my key is the list of 4 digits, the A comma B comma C comma D, or if not list, a tuple, or we can put it as a string based on, again, because in some languages some data structures are not hashable. It can very well be like a CSV, and that we can split and do that, but you get the point. Where we maintain this list, and then once we have a sequence, we run through all the buyers, and then we try to store the maximum value that we can get. In this example, like we store the sum of, and you don't even have to store sum, you can also store a list, but I was thinking like you can store the sum of prices across all the buyers that is there. And here what happens is, as you are generating more and more sequences, you already have a heuristic where and here you can try to keep like the max value always pointing towards it, which means that when you run through all of your sequences and you get this value here, you can just generate a sum and you can keep that sum here. And then when you find the next time you run like some other sequence in the other program, which is X, Y, Z, alpha, you will store that. And then you will keep doing that. And the benefit of this, what I can think initially would be that this will help you maintain a record of all unique 4-character sequences in this giant map. And then you will have all possible answers here. And here also, I think there will be some possible way for us to do some kind of an early returns by optimizing for that. We don't actually have to look through all the sequences, where we can try to calculate some of the sequences and see where the sum is. And if the value is less than that, we just don't store that. We don't need that. And by doing this, once we are done and we are able to reduce, like map and reduce the scope of our problem, at the end, all I need to do is I need to find my max of my value that was there, which is basically the question that is asking like, what is the most number of bananas you can get? And this should help us do this in a fairly good runtime as compared to our brute force solution. So yeah, this is the theory. I think you can see how I even don't know the answer, but these are my best possible tries. I'm going to definitely try brute force. I just love it. It's fun. I think trying to brute force a solution by throwing like a lot of compute at it, basically how our modern LLMs work. But after that, I'll probably see and if how I can optimize that. And yeah, once I'm back, we will do a quick retro and discuss the solution. I'll see you in a bit. And hey, welcome back. As you can see, we have finished the part 2 and we have received another gold star. And now we are closer to finding the chief historian. And this was a very interesting part 2 because I tried brute force and it just did not finish in 30 seconds and I just lost interest. And then I immediately moved on to this pre-computation problem. And this surprisingly worked really well. I was able to get the answer in close to 2 seconds. So there is definitely some form of optimization that we can do here. But I'm pretty satisfied with this considering the large amount of sample space and also that I'm using Python. So I did not look into that. Maybe I think once the challenge is over, I will go back and I will try to see how much more juice we can squeeze out of our code. And yeah, so basically collating all of the patterns and the sums that we can get from that really helped, because in this way, we did not have to maintain the huge sample space for everything. All we had to do was pick one buyer, compute 2000 values, find all the sequences and just dump it in the map. And then just go to another one, find all same. So generate another 2000 tries, find all the 4 sequences and then just dump it all in the map. And then at the end of it, once we were done doing that, all we had to do is we had to just do a sum of this map and try to find like which had the highest price. And once we get that, we had to return the sequence in that and we were able to just put it in and get our answer. And I really had fun solving this problem. And I'm fairly happy that I was able to at least get in the right direction and hopefully nudge you in the right direction as well. And with this, we are at end of day 22. So we have 3 more days to go. And yeah, you can see I'm running a bit behind because making these videos takes more time than I thought it would. And this video series just started as a very simple experiment because last year I was writing blogs and that was also taking a lot of time. So I thought maybe videos would be faster, but recording videos is much simpler, but editing it is on a whole different ball game. But yeah, I have been having really fun doing that, and I have learned a lot on how to edit videos, and I have been trying DaVinci. I tried the Clipchamp, and then I'm now using Adobe Premiere Pro. But yeah, it takes a lot of effort and a lot of time, and it would be really nice if you can like, subscribe, show some love, and share some feedback around how we can make these videos better. So once we are done with the advent of code, I have some videos in pipeline where I would love to see if I can add some values, especially to the software engineers who are like tenured around 5 to 8 years in their careers, because I see there is a gap in the number of resources available for that, and that's when the confusion between the whole management ladder and the software ladder starts. And yeah, I think with that, I will see you in the next video, and you have a really nice day. Bye bye.